All right, moving on, we'll look at polynomial functions. So let's take a look at problem 14. It says consider the polynomial function f of x equal to negative 9x cubed minus x4 squared times x plus 7 to the 6th power times x minus 5. So we've got a linear factorization established with this polynomial. And I want to remember, we'll make a note, every degree in polynomial, right, has n linear factors. So with that, we can start to talk about this polynomial based off its factors. So I want you to, first step, let's count up the linear factors. So how many linear factors do we have in this example? So what are our linear factors of x? So we got x cubed, so we got 3 of the factors of x. We got 2 of the x minus 4s. We got 6 of the x plus 7s and x minus 5. So as we add up those, we got 3, 5, 11, and 12. So we have 12 linear factors in this example. Right? So I already know, based off that, that implies a degree 12 polynomial. All right, so we'll remember that as we're going through this problem. We'll see what they ask us to analyze. But I just want to notice that in the beginning. This is already factored, and that's always our first step. We have a polynomial of higher degree. We want to try to break it down into its n linear factors. So we can talk about the degree of the polynomial. Says state the leading coefficient of the function. So going, our leading coefficient, right, would be this coefficient right here, out leading the polynomial. So leading term would be negative 9x to the 12th power. So that leading coefficient would be negative 9. All right? Make note of that. And again, I'm going to go ahead and mention that. So our leading term, right, is equal to negative 9x to the 12th power. Right, we have a degree 12 polynomial. If we were to multiply them all out, that would be our leading term, our term with the greatest power. Of course, part B says state the degree. So again, the degree is equal to 12, right? Degree, again, is the exponent from that leading term, the largest power that shows up in the polynomial. And here you can see it says state the leading term. So again, our leading term is the term negative 9x to the 12th power. Determine the end behavior. So let's talk about the end behavior using the leading term. So we're going to mention the leading term test. The leading term test describes the end behavior of the graph. So we have a leading coefficient. So let's talk about the leading coefficient first. And leading coefficient, which we recognized as negative 9. So it's less than 0. And our degree, and the degree from this leading term is 12. So it's a even degree polynomial. Well, anytime we have an even degree with a negative leading coefficient, that implies our graph, right, has the ends going the same direction, and they're both going to be going to negative infinity. Now, you'll notice in the middle, I'll put some squiggly marks. The leading term only tells us about the end behavior, right? Doesn't tell us what happens in between the ends. They're in the middle part of this graph. We could have some turning points, which we will. We'll talk about a little later as we further analyze this graph. But that's our end behavior. So left and right tail, right, go to negative infinity. Both go down, right? If they're positive leading coefficient, both ends will go up. Now, if we have an odd degree, right, we have the ends going opposite directions. One will go to negative infinity, the other will go to positive infinity. And if there's a positive coefficient, the left tail is down, right tail is up. If it's negative, left tail up, right tail down. So you do want to review your characteristics from your leading term. But that's the example here with the even degree. Again, even degree, and LC, leading coefficient, less than 0. Our graph right here beneath us. All right, determine the maximum number of turning points. Well, reviewing, every degree in polynomial, all right, lies at most n minus 1 turning points. And what are your turning points? They're your relative min and max points, where your graph changes from increasing to decreasing. So in our example, right, we have a degree 12 polynomial. So that implies at most, right, the maximum we can have is 11 turning points, one less. So that's our max number based off this degree 12 polynomial. Find the domain of the function. Domain of all polynomial functions. Domain is always all real numbers, no undefined values in a polynomial. You're not dividing by x. You don't have even roots. All right, let's find the real zeros of the function and state their multiplicity. So we get into multiplicity, we start to talk about the behavior of the graph at the location of these real number zeros, which are our x-intercept locations. So we're going to go over that as we do this example. We'll see both characteristics come into play. Now, one thing nice about this example, all right, if we want to find the real zeros, right, we set our function equal to 0 and solve for x. So let's go ahead and do that. So with our function, right, we've got negative 9x cubed, right, times x minus 4 squared times x plus 7 to the 6th power times x minus 5 equal to 0. Well, our zeros, right, are from these linear factors, right, from x. So we've got x, right, from that we know x can equal 0. Right, now let's write the multiplicity right here beneath it. So let's ask for multiplicity. Multiplicity is the number of times that factor is being used. So with x cubed, the multiplicity is 3. Right? So we have an odd multiplicity. Now, since it's odd, since that factor is used 3 times, at the x-intercept, so that implies x-intercept point, which is going to be 0, 0, the graph crosses through, right? So it either crosses through or it just touches and bounces off it. So that's with odd multiplicities. Even, it touches, bounces off, we call tangent at that point. And that's what we have in our next example, right? With x minus 4, right? What do we get for our 0 here? So that gives us a real number value of 4, right? X minus 4 equals 0, right? And we can set it up and solve it. Yeah, x equals 4. And its multiplicity, right, as we look at the multiplicity, right? Multiplicity on this one, right? Multiplicity would be 2. Its factor is used 2 times, x minus 4 squared. So with that said, this is a even multiplicity. Now, when it's even, right, the x-intercept point, so the x-intercept, which would be 4, 0, touches. It touches only. All right, crosses through, right? If it's odd, touches if it's even. So again, we're finding our zeros, right? So again, we got 0 and 3, 4, and 2 for multiplicity. And let's go to our third factor. Well, we know x plus 7. Let's find the 0. X plus 7 equals 0 and x equals negative 7. Now it's multiplicity, so let's write the multiplicity beneath it. The multiplicity on that is 6, right? So it's a even multiplicity. So with that, it's even. So we know again at this x-intercept point, right, Write that beside it, negative 7, 0, the x-intercept. The graph touches, right? Won't cross through, but it touches because it's even. All right, let's go to our next and final factor. What do we get with x minus 5? So let's take a look at it together. X minus 5, right over here, x minus 5 equals 0 and x equal 5. And its multiplicity, right? How many times is factor used? One time, right? It's only one x minus 5 factor. So we have a odd multiplicity. So at our x-intercept point, which would be at 5 on the x-axis, right, we know we're going to be touching or actually crossing through, right, at this point. So it crosses through when it's odd, touches when it's even. So with that, we can gather information to build a sketch of this graph. So that's what I want to do next. So let's use this information. So let's go ahead and I'll graph this one in blue. All right, let's put a graph over here. So we have a x-intercept at negative 7 on the x-axis. So we'll go ahead and plot negative 7. So here's that point, negative 7, 0. And then we have a x-intercept at the origin. So let's go ahead and put in the origin here, 0, 0. We have an x-intercept over at 4 on the x-axis. So I'll put 4 on here. There's 4, 0. And then we have one at 5, 0. So I'll plot that point, 5, 0. But they're my x-intercepts. Now, based off my end behavior, so we know the left tail comes from negative infinity, and the right tail goes to negative infinity. Both ends go down. Now, we said at negative 7, all right, we noticed it should touch and bounce off. So as I'm coming from negative infinity, right, we're going to bounce off this point. Well, bounce off means we form a turning point, right, at that point. So we have a turning point at that x-intercept. That's a max point. And then at 0, we had an odd multiplicity. So as it comes back up to pass through the point 0, 0, and again, it crosses through there. All right. Well, we have the 0, 4 that had an even multiplicity. So as it comes back down to touch, not cross through this point, right, bounces off it. And then it goes to, 5. So as it goes back up and comes back down again, right, we can see our graph. So here's our left tail to negative infinity and a right tail to negative infinity. So there's a sketch of this polynomial function. So here's a graph of f of x. So again, I want you to notice, again, this information, right, crosses through, right there. And again, with the even multiplicity, at negative 7, it touches. So you can see that it touches there at that point. And maybe we'll look at it. But again, I just want to show that information. So it crosses through at 0, right? It touches at 4 also, even multiplicity. So there's our graph, right, of our function, f of x. All right. Now, on what set of x values is this function greater than or equal to 0? So let's give the intervals. So now we have the graph in front of us. We can easily see that. So where does it equal 0 or where is it positive? So where is it on the x-axis and where is it above the x-axis? So with that, we got x value of what, negative 7? X equal negative 7 produces a value that's greater than or equal to 0. All right? Or we can also go over here to where? Now, between negative 7 and 0, our function is negative, right? It's below the x-axis, got negative y values. But when I look between 0 and 5, right, between 0 and 5 on the x-axis, our graph is either touching the x-axis or above it. So let's write that interval. So all x values greater than or equal to 0 and less than or equal to 5. So there's our interval, right, of x values. So we got negative 7 and we got 0 to 5. All right, now let's do the negative. That's our next question here. Where are the x values for this function being negative? So where is it below the x-axis? All right, now less than 0 says it's not equal to 0, so we don't want to include -7. But yeah, x greater than -7 and less than 0, right? We see it below. Of course, we also see it from -infinity to -7, so we should include that interval. Right, from the left to -7, the graph is, of course, negative values. And where else it's greater than 5, it's less than 0, so 5 to infinity. So again, you see a graph right below the x-axis. Right, so again, that's analyzing the graph of the polynomial. So doing that based off key characteristics. The leading term tells us about the end behavior, and our zeros and their multiplicity allow us to sketch the graph of the polynomial. So I hope that helps. We'll do another example here in a little bit. We'll stop there for now.